We're going to start talking about gas stoichiometry, and to do that we're going to kind of break it down and go kind of slowly bit by bit here, because some of this is gas laws, ideal gas law, like PV equals nRT, and some of it is stoichiometry. So you just have to be able to tell, at what part do you need which of those two components. So let's look at the first question together, and then I'll just ask that we'll pause the video, or the sub will pause the video, and you can try some of this on your own, and then I'll show you the correct correct way to do it. But I do ask that, just like if I were lecturing in class there with you guys, just make sure that you're attempting the problem. I don't mind if you work, talk a little bit with people sitting next to you. In that time the video is paused, try to figure it out. Do your best before watching me do it. Okay, so 1A and B go together. That's why I've got them kind of boxed in like that. And then 2A goes with 2B, and then 3 is its own thing. So let's start with 1A, and hopefully we'll be able to see how these two go together eventually. So 1A says how many moles of CO2 would occupy 325 milliliters at 0.950 atmospheres and 296 kelvins. Okay, so we are just looking to first rearrange PV equals nRT. And we're trying to solve for moles, right? N. So our new equation, if we divide both sides by R times T, that's going to get moles by itself. So N equals PV over RT. And then I just have to plug in the values that were given to me in the problem. So my pressure is 0.95 atmospheres. My volume is 325 milliliters, but I want you to think about how many liters that would be. Basically, we're just taking that number and dividing by 1,000 if we want to go to liters, right? So it would be 0.325 liters. And then on the bottom, our R value depends on the pressure unit, right? So if you look back in your notes, you should be able to figure out the R value for an atmospheres. It's a constant, so it's always going to be, as long as we're in atmospheres, 0.0821 atmospheres times liters over moles times kelvins. And then our temperature has to be given to us in kelvins, or if it's given to us in Celsius, we have to add 273, but it's already in kelvins. So 296. And hopefully you already have a calculator out. If you don't, go grab one. Just make sure that when you do this, that you either multiply across the top, write down your answer, then multiply across the bottom, write down your answer, and then divide your top answer by your bottom answer, or just go control divide on the calculator and it'll put it to you in a fraction form. You just have to fill in the numbers and your order of operations will be done right. So please go ahead and calculate that. We'll go ahead and pause it there, please. Okay, and hopefully you found that you have an N of 0.0127 moles of CO2, and make sure that you label that completely. So include your what it is that we have moles of. That's going to become very important in gas stoichiometry. Now, so far this isn't really stoichiometry. This is just ideal gas law, PV equals nRT. If we then take this down below to 1B, the question continues and it says how many grams of propane, C3H8, would we need to burn in order to produce that much CO2, meaning the number that we got from the previous question, 0.0127. Okay, so we are going to approach this problem just like a stoichiometry problem. So we're looking for grams of propane. So think about, what would I need in order to get grams of propane? I would need moles of propane. And then to get moles of propane, if I'm not given anything else in 1b, I am given some pretty important information in 1a, or at least I found some pretty important information in 1a. I found that I have this certain number of moles of CO2. And I was given a balanced equation, so I should be able to come up with a relationship between moles of CO2 and moles of propane. So I should be able to go from moles of CO2 that I just calculated to moles of propane, and then to grams of propane using the periodic table. So go ahead and give that a shot. We'll pause the video here and see how you can do with that stoichiometry. Okay, so this part is just stoichiometry. So hopefully you started with the number of moles of CO2 that we calculated in the previous problem, 0.0127, and then you went to moles of C3H8, just like we said in our plan, so mole to mole conversion, and then from moles of C3H8 we go to grams. That's going to be using the periodic table. So let's go ahead and fill in our numbers. Going to the balanced equation, it looks like I have 1 mole of propane for every 3 moles of CO2. And then if I go to the periodic table, 1 mole, remember we always put the number 1 in front of moles when we're converting between moles and grams, right? We only use the coefficients from the balanced equation when we're going moles to moles. We put a 1 in front of moles when we're going between moles and grams. And then if I go to the periodic table and I add up 3 carbons and 8 hydrogens, I should come up with about 44.11. Okay? And if I plug that into the calculator, I'm just going to do that with you, 0.0127. So 0.0127 times 44.11 over 3. And I should get 0.187 grams of C3H8. So hopefully you got that answer too. You can see here, this basically just becomes one big gas stoichiometry problem. Going back to the starting question, I was given volume, pressure, and temperature of a gas, and then I was asked for grams of a different substance in the, and given a balanced equation. So in this case, we used the ideal gas law first, and then we found a number of moles, and we used that to convert to grams of a different substance. So then if we look at 2, I'm going to tell you we're going to be doing the exact opposite. So this time it says how many moles of oxygen would you expect to make by decomposing 28 grams of KClO3, potassium chlorate, in the following equation. So in this case, and once again we're given the balanced equation, but in this case we're given, at least to start with, the number of grams of potassium chlorate, and it's asking us for moles of oxygen. And it doesn't say anything about temperature and pressure at first. Okay? So it looks like we're going to be doing the stoichiometry first. So we're going to be going from grams of potassium chlorate to moles of potassium chlorate. And then the question is asking us for moles of O2, oxygen. So go ahead and do that on your own right now or with a partner, and then I'll show you the answer for this part. Go ahead and pause it here. Okay, so there you can see what I got, 0.349 moles of oxygen. And so that would be starting with grams of KClO3, and then since oxygen is a gas, the next question is going to use that information. How many liters of oxygen would this occupy at 24 degrees Celsius and 105 kPa? So if it's giving you the moles up here, moles of oxygen, and it's asking you for liters of oxygen and giving you the temperature and pressure, then this is just an ideal gas law problem. You have moles, you have temperature, you have pressure, and you want to know how many liters. You want to know the volume. So go ahead and see if you can rearrange PV equals nRT without plugging in numbers. Just rearrange that to solve for volume. Go ahead and pause here, please. Okay, so to get volume by itself, we would divide both sides by P. And so we get V equals nRT over P. And so I'm just going to plug in the numbers. The N value, and again, this is for oxygen, because we're looking for volume of oxygen. So the N value here would be the number I just calculated, 0.349 moles. The R value, if my pressure is in kPa, the R value, again, this is in your notes, but it's 8.31 kPa times liters over moles times kelvins. The temperature is in Celsius, so we have to do kind of off to the side here, 24 plus 273, right? So that gives us 297, right? Okay, so and then my pressure was 105 kPa. Okay, so that should give us our volume. Go ahead and pause here and calculate and see what you get. Okay, so I got 8.1995. So it looks like 3 sig figs, so 8.20. And if I go through, and I didn't talk about canceling units earlier, but if I go through and cancel moles, we'll cancel there, kelvins, and then kPa, so I am left with liters, which would be the unit for my answer. So 8.20 liters of, and I really should label it liters of O2. Okay? Alright, so let's take a look at the last problem here. And this one is shorter, but it's actually a little bit more difficult because on problems 1 and 2, I broke it down into parts A and B. We're going to have to do just as much work for problem 3, but I'm not breaking it down for you here in the question. Okay, so let's take a look at this, what this means. If I'm given here, I'm asked for, how many grams of N2, right? So that's what I need to know. I'm given 400 liters of NH3, 15 degrees Celsius, and 835 mmHg. So let's take a look at which of the problems up above, 1 and 2, this one best compares to. So I guess the first point to this is the ultimate question is how many grams of something, right? So if you look here at problems 1 and 2, on problem 1, we were given a volume, temperature, and pressure, and so we were finding moles first, right? And then after that, we were asked for grams. So we started with volume, pressure, and temperature, and we went all the way to grams of a different substance, okay? And so in this problem, because we were looking for grams, and we were given volume, temperature, and pressure, we started with the ideal gas law, then we did stoichiometry, right? If you look at question 2, A and B, here we are starting with grams and being asked ultimately, we go all the way down to question 2B, for volume of a gas. So because we are given grams and we're ending with liters, we are going to do the opposite. We started with stoichiometry and then we use the ideal gas law to find liters. So if I look at question 3, which problem, 1A and B or 2A and B, in other words, number 1 or number 2, is this problem closer to? If I'm asking you for grams and starting you with volume, temperature, and pressure. Go ahead and pause and think about that for a second. Okay, so if I'm asking you for grams and giving you volume and temperature and pressure, I think this one more closely resembles question 1, 1A and 1B, because this is kind of the same thing. I'm asking for grams ultimately in the end, and I'm starting with the volume, temperature, and pressure. So that means that question 3, because I'm asking for grams and given volume, temperature, and pressure, I'm going to use the ideal gas law and then stoichiometry. It's not going to be like question 2, where we started with stoichiometry and then went to the ideal gas law. Okay, so let's go ahead and see if we can figure out this problem. So again, if it's like question 1, which one are you going to start with? You're going to start with the ideal gas law. You're going to be using this information, right? And the question, though, or the problem with this is it's asking for grams of one thing, and it's giving you volume, temperature, and pressure of something else. So what I want to do is kind of plan this whole thing out backwards. Okay, so if I want grams of N2, just like when we did stoichiometry, if I want to plan this out, I have grams of N2 that I'm looking for. What would I need to get first? What would be the previous step? So hopefully you said moles of N2, right? Okay, so now it turns out that nitrogen is a gas, and so you might be thinking, well, I can just use the ideal gas law to find the moles of N2. The problem is I'm given this information, this 400 liters of NH3, so I'm not given information about the volume, temperature, and pressure of nitrogen. I'm given the information about another substance in the equation. Okay, so I'm going to have to use that other substance, NH3. So I'm going to have to figure out moles of NH3. So far this looks like stoichiometry, right? Just moles to grams. And we do have a balanced equation, so we will be able to go from moles of one thing to moles of another, right? The thing that makes this a gas stoichiometry problem is we don't have moles of NH3, but we do have volume, temperature, and pressure of NH3, right? So we can actually use the ideal gas law to go from the liters of NH3 to moles, because we know that, rearranging the ideal gas law, N equals PV over RT, right? So that's going to allow us to go from here to here, as long as we also know the pressure and the temperature. And then the rest, all of this stuff, is just stoichiometry. So see if you can right now, using the volume, temperature, and pressure, figure out the number of moles of NH3. And it's very important that you understand what you're calculating. And so when you do this, you want to label it N of NH3. So put NH3 as a little subscript. And then I'm going to rewrite my equation. Here's why that's so important. I made that line a little long here. The reason that that's important is when I get an answer, when I plug in my pressure, volume, and temperature, it's going to be a number of moles, but it's not going to be moles of N2. It's going to be moles of NH3, and it's very important that I understand that difference, because if I think that what I've calculated is moles of N2, I will have skipped a step. All right, so let's try the problem and see if you know what I'm talking about here. So just find the moles of NH3 by plugging in the variables given to you in the problem. Take about 3 or 4 minutes to do that. Go ahead and pause here, please. Okay, so there's my setup. You do want to pay special attention to two things here. The R value, and this is in your notes again, but mmHg is different from kPa in atmosphere. So if we're in mmHg, millimeters of mercury, we're going to use 62.4 for our R value. The other thing, of course, is 15 degrees Celsius has to, we have to add 273 and we get 288 kelvins. Okay, so when I do the multiplication division here, I get 18.6. And that's moles. Okay, so but here's the important part. You can't stop there with just labeling it moles. We have to say what this is moles of. Remember back here we paid special attention to labeling this NH3. All of this stuff, particularly the volume, is describing NH3, not anything else in the equation, and especially not N2. All right? And that's important for the next step. So I'm going to label this moles NH3. Very important. Okay? So right now, I did all of that just to make this one step from liters to moles. But now it should be pretty easy, because now we should be able to do the stoichiometry to go from moles of NH3 to grams of N2. So if I take my answer down here that I just got, 18.6 moles of NH3 over 1, and see if you can go ahead and take that to grams of N2, which the problem is asking for. Okay, so there's my setup. My moles of N2 and moles of NH3 would be my first little step, my mole-to-mole conversion. And from the balanced equation, there is 1 mole of N2 for every 2 moles of NH3. And then going to the periodic table, 1 mole of N2 is equal to 28.02 grams. And then if I do the multiplication here, I get 260 rounded to, once again, 3 sig figs, looks like 261 grams of N2. And we're going to talk next time a little bit about how do we do a mental check to see if this answer makes sense. But this is the correct answer. That mental check, of course, we'll want to do every time. We will go ahead and pick up with this next time. We won't have any more problems for homework, but we'll do several more in class to start class on Wednesday, and then we're going to head into the lab.